Okay, welcome back everybody. Today we're just going to have a quick video about the electric field inside conductors and insulators. So if you finish the electric field lab, this is related to the last question in that lab where it asks you about the field inside a conductor. So let's just talk about a solid conducting surface. Let's say that this is a sphere. I'm not going to try to draw in 3D, but let's say it's a sphere, right? I know that charge wants to spread out on the surface as evenly as possible, okay? And since charges repel each other, they want to be as far apart away as they can, right? So I know that they're going to push on each other and push on each other until they are spread out as far as they could possibly spread out. And then they're going to stop. They're going to stop moving, okay? So we're going to call this static equilibrium. Means the charges on my conductor have come to a rest, okay? And that tells me some very important things. First of all, that tells me that the electric field inside the conductor is equal to 0, okay? So why is that? Why at any point in space inside my conductor is my electric field equal to 0 if I do it at any point in here? So to answer that question, think about what would happen if there was an electric field inside the conductor. Let's say that at this point my electric field was 5 newtons per coulomb. What would that do to the charges on the surface of my conductor? Well, if it was an electric field, a positive charge would want to move away from it. So it would end up pushing my charges around and they would move, and then they would no longer be in equilibrium, right? Obviously that's not what we want. So I'm trying to undo this to get that away, but I think I'll just leave it. So that immediately tells us that there cannot be an electric field inside the conductor, otherwise the charges would move and that would violate my static equilibrium, right? So I want to show this to you guys. I've got a little Java applet here. So I can move, this is for a conductor and this is the electric field. We can see that away from the conductor, if I move this, you can see that it follows this R squared law, right? And ignore the fact that it says negative 20 for the field down here. All that's telling me is that the charge on my conductor is negative, right? But actually, if I move closer, the magnitude gets bigger, as we see with the R squared. And if I go inside the conductor, I immediately, boom, I immediately drop to 0, anywhere inside the conductor. Now an insulator is a slightly different story. For an insulator, we can spread charge evenly throughout the entire surface. So let's say that I have an insulator. There's my scroll bar. Insulator, hooray. So it's going to be this solid ball or whatever. It's a solid hunk of material. Or it could be hollow, it doesn't matter. But I can spread charge evenly throughout my insulator. And what we're going to see is that actually is going to make the electric field a little bit different. So I want to find the electric field as a function of distance. Here's inside my insulator and then outside of it. Right? So let's go back to our applet and look at this. Let's choose Insulator Field, and if I move this, we can see that it's getting bigger as we get closer, following the inverse square law like we would expect. And then once I get inside, it linearly drops off to the center. Now, we're not really going to get into why that's linear, but it has to do with superposition, right? And the summing of all the electric field due to all these different charges. Right in the middle the electric field is equal to 0 in the middle because all the charges cancel each other out, right? You saw that with your lab that you did, with the electric field lab. As you move towards the outside, though, these charges on this side don't push as hard as these charges on this side, right? Because we're closer to it on this side. So the electric field gets stronger. The reason it's linear has to do with the fact that it's the geometry of the sphere, right? So that's the electric field inside and outside of conductors and insulators. So you can see that one more time. And that's all for this video.